In 1666, during a horrible pandemic that forced the closure of businesses and schools throughout England, a bright young math student from Trinity College in Cambridge sat beneath an apple tree on his family farm while contemplating the esoteric subject of celestial mechanics, the physics of the heavens. At the time, the heavens and the earth were thought to obey two drastically different laws of motion prescribed by Aristotle. Motion on Earth was evanescent and governed by transient forces within our intellectual reach, while the motion of the heavens was eternal and governed by arcane forces beyond our grasp. The story goes that while the student was pondering the orbit of the moon around Earth, an apple fell from the tree and struck him on the head, delivering a profound epiphany. In that moment, the young Isaac Newton realized that the same gravitational force which pulled down the apple is also pulling down on the moon. This story of revelation is probably just a story that Newton made up, but the iconoclastic scientist could not have chosen a better fruit to symbolize the incredible knowledge he discovered about gravitation, which united the physical laws of heaven and earth and enabled humans to visit other worlds.
Make sure that you've got your feet underneath you.
Hello everyone, I'm Jesse Mason, and in this video, we'll learn about gravity and orbits. That seminal year on the Newton family farm yielded 4 major discoveries that rocked the world of science. The first was his laws of motion, which upended 2 millennia of thinking on the subject. Aristotle had people convinced that forces cause motion, but Newton demonstrated unequivocally that forces do not cause motion, but rather change motion. Much of introductory physics consists of the innumerable applications of these 3 thrilling laws. Newton's second discovery explained the composition of white light, which had always been regarded as the purest form of light. Through clever experimentation involving prisms, Newton showed that colored light is actually the pure form of light. That year he also discovered a useful form of math, which he called fluxions, but we now call calculus, which helped him explain the changes in motion that his 3 laws described. His fourth discovery of 1666, delivered by messenger apple, was that the phenomenon of gravitation is universal. Newton explained this final discovery using a wonderful thought experiment featuring a powerful cannon on a mountaintop. In honor of Newton, we'll use apples instead of cannonballs. Suppose an apple is launched from a low-power cannon atop the mountain. The apple would arc to the ground a short distance from the base of the mountain. Now, a medium-power cannon would launch the apple even further along the curvature of the Earth. A high-power cannon could get the apple halfway around the planet. You see where this is going? If we had a cannon powerful enough, and if our atmosphere wasn't such a drag, we could give that apple an initial velocity so great that the arc of its trajectory would match the curvature of the Earth. So, as the supersonic apple falls toward the ground curves away from the apple at exactly the same rate. And eventually, the apple would return to the mountain from whence it came. And if we could somehow move our mountain out of the way, the apple would become a satellite, orbiting Earth at the same altitude as the elevation from which it was launched. The moon, Newton realized with this thought experiment, is simply Earth's natural satellite, falling toward the Earth like the apple, because it must be attracted toward the Earth like the apple. Gravitational attraction does not belong to Earth, it belongs to the universe. That's the heart of Newton's universal law of gravitation. Simply put, massive bodies, no matter their separation, are attracted to other massive bodies. Now let that sink in for a second. So this chair is attracted to this desk, the mountain is attracted to the apple, and I'm attracted to the moon, to Saturn, to a black hole we imaged not long ago in a galaxy far, far away? Yep, you can't feel it, but everything with mass is pulling on you. The idea that gravitational attraction applies to all bodies and extends all the way across the cosmos was a hard pill to swallow. But this elegant law explained the motion of the moon, the motions of the planets, and the motions of moons around other planets. And it accurately predicted for the very first time in human history the arrival of a comet. The simplest case we can depict graphically is that of two spherical bodies with force vectors indicating mutual gravitation. These two forces are equal in magnitude but opposite in direction. Equal but opposite. Does that ring a bell? Yes, these two forces do constitute a Newton's third law pair, which means not only does the Earth tug on the moon, but the moon tugs back on the Earth. Of course, we have an equation that quantifies Newton's qualitatively incredible law. Fg equals g times m1 times m2 over r squared. Here, Fg is the gravitational force in newtons, m1 and m2 are the body's masses, r is the distance between the body's centers of mass. We'll learn more about center of mass later, but for now it's sufficient to say that the center of mass of a spherical body like a planet or a star is at their geometric center. And lastly, big G is the gravitational constant, which is equal to 6.674 times 10 to the negative 11th Newton meters squared per kilogram squared. We'll call it big G to differentiate from little g, the acceleration due to gravity. Big G is one of a couple dozen constants that we will encounter on our learning journey together. It is far more fundamental than little g, which, when we get to force fields, we'll learn actually comes from big G. Big G is one of a couple dozen constants that characterize our entire universe, which, as far as we can tell, don't change with respect to space or time. If big G were just a fraction of a percent larger, making the gravitational attraction a little bit stronger, or a little bit smaller, making the gravitational attraction a little bit weaker. None of this. The chair, the desk, Saturn, you or I, none of it would be here. And the same goes for the other physical constants. Is our universe a finely tuned instrument for playing the song of existence and of life and consciousness? Sounds like it. Are there other universes out there? Playing out of tune, so to speak? Some scientists think so. Perhaps there is an infinite orchestra of universes out there, playing an unfathomably complex symphony of existences, and we just happen to be playing first violin at the concert. What a thought. Now, before we tackle a problem using Newton's universal law of gravitation, I'd like to point out that nu log is our first inverse square law, which is to say, this is the first of several laws we'll encounter in physics, which the strength of the phenomenon, or flux as physicists refer to it, decreases with the square of its distance. So if we were to double the distance between the two bodies here, the gravitational force between them would be a quarter of its original strength. Tripling the distance would decrease it to a ninth of its original strength. Exponentials tend to explode in size, which is why massive bodies like our moon have little effect down here on Earth. Sometimes, though, those little effects can add up, which is precisely the case for our moon and the oceans. The tides, Newton correctly observed after discovering his gravitational law, are a direct consequence of the tiny pull exerted by the moon on zillions of tiny water drops in the ocean. Okay, let's tackle a problem using our new tool. Let's find the speed an apple would have to be moving to stay in orbit around Earth. To make this silly problem a little bit more realistic, we'll elevate the apple to, I don't know, let's say 420 kilometers, so very high that atmospheric drag won't be an issue for our apple. First things first, let's draw a picture. We always DAP, draw a picture, when solving a physics problem. So here's the Earth, and here's our apple moving in circular orbit around the planet, traveling at some terrifying speed. Definitely wouldn't want to get hit in the head by that apple. Since we're looking for the speed, we'll give it a dollar sign, indicating once we've found that value, we are in the money. Speaking of values, let's write the only value this problem lists, which is the altitude of the apple. We'll assign the variable h for elevation. And if you're like me, you want to convert that value right away to meters. Equations say yes to the MKS. Units, that is. Okay, we've got a bit of room left, which we'll save just in case we need to look up any other constants for our problem. Yes, we will need the gravitational constant. Why don't we write that right now? Big G equals 6.674 times 10 to the negative 11th Newton meters squared per kilogram squared. All right, on to the equation step. This is a new log problem, so we'll start with the general form of the equation. And then we'll modify it to reflect the two bodies in question, the Earth and our astronautical apple. Now, before we start digging up Earth's mass, etc., let's look at what we know about the gravitational force here. We don't have a value for this force, but we do know that it is responsible for the apple's uniform circular motion around the planet. Recall that uniform circular motion is characterized by constant speed with a constant perpendicular acceleration, or centripetal acceleration, which requires a centripetal force. The centripetal force that moves a body in uniform circular motion can be calculated by multiplying the mass of the moving body by its speed squared and dividing by the radius of its curve. The gravitational force is the centripetal force on the apple. So we can write mv squared over r equals big G me ma over r squared. This m here is the mass of the apple, so we'll add that subscript. And now we solve for v. We'll multiply the whole equation by r over ma, dividing out one of these r's and both masses. And this yields an amazing result. The mass of the apple won't affect its orbit. It could be the size of a football field, and so long as it's moving at this speed, it'll maintain an orbital altitude of 420 kilometers. By the way, to get rid of that square, we take a square root of both sides. Okay, now what about this r here? Remember that r is not the distance between each body, but rather the distance between the centers of mass for each body. So we need to add the radius of each body to the distance between them to get the distance between their centers of mass. Even if it were as big as a football field, the radius of the apple is insignificant compared to its altitude and Earth's whopping radius, so we'll ignore it in our calculations. And then we can finally look up the mass and radius of the Earth. We'll put both of those next to our picture in case we make a mistake and need to retrace our steps. And we'll convert 6,371 kilometers to meters. And the mass of the Earth is about 6 trillion kilograms. Yeah, it's kind of a big deal. Okay, we insert our values into the equation, big G, the mass of the Earth, over the sum of the two radii, and just a little bit of equation feng shui here. Get that out of the way. And before we grab our calculator for the plug and chug, let's do a dimensional analysis. The meters divide out one of those meters, kilograms divide out one of those kilograms. And remember that a Newton is a kilogram meter per second squared. So when we substitute in a kilogram meter per second squared for the Newton, we get a kilogram meters squared per second squared in the numerator and kilograms in the denominator, which divides out, leaving us with meters squared per second squared. Take a square root, we get meters per second. Okay, now for some plug and chug. And we get 7,660 meters per second. Holy applesauce, that is one fast fruit. 7.66 kilometers, that's about 5 miles a second. That speed would take you from Detroit to Orlando in less than 5 minutes. Is that right? Does an object orbiting at 420 kilometers up move at 5 miles per second? Well, if you were to ask these 4 research scientists how fast they needed to be going to catch up to their orbiting lab, they would tell you that is precisely how fast it's moving. The International Space Station is a flying laboratory the size of a football field, 420 kilometers above Earth's surface. The ISS is moving so fast that astronauts aboard are treated to several sunrises each day. How many sunrises, you ask? I'd ask the astronauts, but they've been very busy lately and haven't been returning my calls. Let's figure it out for ourselves. First, let's draw a picture. Here's Earth, and here's our our space station. By the way, isn't it cool the leaves of the apple and the solar panels of the space station basically do the same thing? Turn sunlight into usable energy? I think that's pretty cool. Anyway, we'll use the speed equation to tackle this problem. Speed equals distance over time. For t, we'll be using an Earth day, a 24-hour period. For d here, we want to incorporate the number of sunrises, which is the number of revolutions the ISS completes in a day. We'll call that n, which is the value we're looking for. Now, assuming a circular orbit, the distance traveled for one revolution is the circumference of that orbit. So, the distance traveled in one day is just the number of revolutions made in a 24-hour period times the circumference of the orbit. And circumference, of course, is just 2 pi r. Okay, we've broken this down as far as we need to because we have all the values except for n, the one we're looking for. So we need to solve for n by multiplying both sides by t over 2 pi r, which gives us n equals vt over 2 pi r. And this r is the sum of the Earth radius and the altitude of the space station. We'll rewrite this. Last thing we need to do is convert one day to seconds. Equations say yes to the MKS. So after a quick conversion, we get 86,400 seconds in a day. We'll do a quick dimensional analysis before we grab our calculator. And the meters divide out, and so do the seconds, which is good because we're looking for just a number. Now we can plug and chug, inserting our values. And we get 15.8 sunrises. Does this value answer our question? How many sunrises do they see? Wait a minute. Can we have 15.8 sunrises in a single day? No, that makes no physical sense. You can't have partial sunrises. So the astronauts aboard the ISS see 15 sunrises on some days and 16 on others. Can that space station stay up there forever? As long as we're willing to keep going up there and giving it a little boost. You see, it turns out that even though the atmosphere is very tenuous at 420 kilometers up, the collisions that do occur with the particles that mill about at that altitude cause a very tiny amount of drag. And remember, tiny things can add up over time. So over time, it reduces the velocity of the space station. Going back to Newton's thought experiment, reduced velocity causes a decrease in altitude, bringing it in contact with denser atmosphere, which increases drag, which reduces velocity, which, well, you get the picture. It's a gradual death spiral for the space station, culminating in a fiery re-entry into the Earth's atmosphere like this one. This is a picture of our 1970s space station, Skylab, re-entering Earth's atmosphere and some of the remains that were found in Australia. To keep our ISS from going the way of Skylab, visiting rocket ships fire their rockets while attached to the space station to help it regain lost altitude. Suppose we were to keep firing the rockets, drifting further and further from Earth. Eventually, we'd reach the orbit of the Moon, which is exactly what we did in 1969 with Apollo 11, humanity's first lunar landing. And we coordinated the rendezvous with just the celestial mechanics that Newton gifted us. And we are going back in a few years with a space station that's being built just for lunar orbit. Gateway, the forthcoming lunar space station, will be an orbiting outpost for long-duration visits to the Moon, and a stepping stone for our next giant leap, which will be sending humans to walk on Mars. How fast will the Gateway space station need to be going to match the orbital velocity of our Moon? Well, we're dealing with the same physics here, so we can just borrow the modified equation from our apple problem using a few different values for the plug and chug. For r now, we need to use the sum of the Earth radius, the Moon radius, and the Earth-Moon distance. Looking up values for the Moon radius and the Earth-Moon distance and converting to meters, Our equations say yes to the MKS. And inserting our values into the equation, big G, the mass of the Earth, and the sum of the two radii and the Earth-Moon distance. A little dimensional analysis, just to make sure we'll get meters per second. And it looks like we will. Good. And then we plug in chug, which gives us an orbital speed for the moon of 1,010 meters per second. So is that how fast Gateway will need to be traveling when it gets to the moon? Not so fast, or perhaps not so slow. Remember that the orbital speed of the space station is set by the mass and radius of the body being orbited, as well as the orbital altitude. So once again, we need to solve our modified equation here with different values. The m in the equation now represents the mass of the moon, because the Lunar Space Station will be orbiting the moon. Here's that value, by the way. And the r represents the radius of the moon, plus the radius of the space station, which we'll ignore for obvious reasons, plus the altitude. There's no atmosphere on the moon, which means no atmospheric drag, so orbital decay and fiery death spirals aren't much of an issue. So long as we're higher than the highest mountains on the moon, which are about 5 kilometers, we'll be fine. 100 kilometers would give us plenty of clearance, but let's use 111 kilometers in honor of the world's best wingman, Michael Collins, who traveled all the way to the moon in 1969 and watched his buddies Neil and Buzz trounce around on the lunar surface 111 kilometers below him. A little plugging and chugging now, using our values that we have, and we get 1,629 meters per second, which is slightly faster than the moon's orbital velocity, but quite a bit slower than our original Earth orbit velocity. Wait a minute, so there are two changes in velocity, or delta V's, to move a body from our low Earth orbit, where it's moving at 7.7 kilometers per second, to our lunar orbit, which requires a speed of 1.0 kilometers per second? Yeah. We would need to fire the rocket to propel us there. Rocket scientists call this a translunar injection burn. And then when we get there, we need to turn the rocket around and fire it again to decrease our speed and insert ourselves into lunar orbit. Rocket scientists call that a lunar orbital insertion burn. Now, if our rockets were to fail on the second burn, we would completely miss lunar orbital insertion and fly right by the moon. If timing and aiming weren't tricky enough already, remember that we're shooting for a body 250,000 miles away, moving to the side faster than a speeding bullet. This is an impressive feat by today's standards, but a mind-blowing feat in 1969 when Apollo scientists were using less sophisticated computer circuitry than you or I have in our pockets. And I'm not talking about our cell phones, I'm talking about our key fobs. I think it's impossible to overstate the triumph and significance of this moment for humanity. The moment when humans first stepped foot on another world. This will be remembered for hundreds and thousands and hopefully millions of years.
Armstrong is on the moon. Neil Armstrong, 38-year-old American, standing on the surface of the moon. On this July 20th, 1969.
That's one small step for man, one giant leap for mankind.
Now, suppose we were to leave the rockets on during that first burn and just kept speeding up, leaving the moon in our rear view mirror. Well, if we had enough rocket fuel, we would eventually reach a velocity so high that we would escape the grasp of Earth's gravity and leave Earth's orbit altogether. This so-called escape velocity can easily be calculated, but only once we've learned about our next topic in physics, energy. That's all for Gravity and Orbits. I'm Jesse Mason. Thanks for watching. I'm looking forward to continuing our learning journey together in our next video. And until then, happy learning.